I'm here to talk about a really devastating disease. It's created a huge impact on basically everyone's lives. It's killed some of the most well-known celebrities, the most notable Steve Jobs recently. It's called pancreatic cancer. And pancreatic cancer is a devastating disease. Only 5.5% of people who are initially diagnosed will survive after 5 years. And one of the main reasons due to this is that usually once it's diagnosed, the cancer is spread around the body when the patient has a very small chance of survival. And in order to prevent this late detection, we need a method for early detection, meaning a simple, rapid, sensitive, versatile, and minimally invasive sensor for the early detection of pancreatic cancer. And so there are a variety of proteins that are found in the blood of patients who have pancreatic cancer that are at elevated levels. I chose to say one called mesothelin. Mesothelin, it's highly overexpressed by pancreatic cancer, but not by healthy tissue. But in addition, it's highly overexpressed by these things we call non-invasive precursor lesions, meaning if you can detect this protein, you can detect pancreatic cancer before it becomes invasive, possibly making the survival rate jump above 50% rather than a measly 5.5%. So in order to detect these ultra-low concentrations of mesothelin in your blood, I employed these carbon nanotubes, atom-thick tubes of carbon. And they're really the superheroes of science and material science because they have these broad applications which lead to inexpensive biosensors. In my case, I was looking at how the distance between neighboring carbon nanotubes highly impacts how electricity is transported along them. And so I'm really fascinated by carbon nanotubes. I was reading this really interesting paper in my biology class, and all of a sudden, we were learning about these new things called antibodies, organic molecules that actually bind specifically to one protein. In my case, it would be to mesothelin, kind of like a lock and key. And so then I thought, in my biology class, I was just sitting there behind my desk looking at this little paper, and thought, what if I put this antibody in a network of carbon nanotubes, just wildly on a whim? And then it hit me. Amazing. I was very, very happy. My biology teacher wasn't as happy when she found me reading a paper instead of writing an essay on biology class. So then, what I had to have then is a substrate that you can basically support this network of antibodies and carbon nanotubes. And I thought it had to be porous to take up this aqueous solution, but also it had to be inexpensive and readily available. Filter paper, it fulfills all of these. And basically all you have to do is create a uniform dispersion of these antibodies and carbon nanotubes. They're just floating around, chilling out. And then you basically just dip coat your sensor, making it really easy to produce. And so here's a visual depiction of the sensor being created. And how you test it, basically, it only requires 1/6 of a drop. And you just put it on, and then you just measure the change in electrical potential, just an electric parameter. So then, in order to detect pancreatic cancer from the detection of this protein, basically what you have to do is you have to establish what we call a cutoff level, where anything above that level of mesothelin is considered positive, anything below we consider negative. And so usually it's 10 nanograms per ml for mesothelin, so that's what I chose. And so then I ran in vitro study just to make sure it was working pretty well, and it worked spectacularly, actually. And then we went into actually testing human samples. We had patients who had pancreatic cancer and then also the non-invasive precursor lesions. You can see they all fall in this range of 18 to 28 nanograms per ml. That's well above the 10 nanogram per ml cutoff. All of these would be found positive by my sensor, meaning that it had 100% sensitivity towards pancreatic cancer. Then we had patients who did not have pancreatic cancer. They are either perfectly healthy and skipping around, or they had chronic pancreatitis, meaning an inflammation of the pancreas, the disease most often mistaken in diagnosis of pancreatic cancer. All of these you can see are below 10 nanograms per ml, meaning that they would all be found negative by my sensor, meaning that it had 100% selectivity towards pancreatic cancer. So it was giving near perfect diagnosis of pancreatic cancer, thus revolutionizing how we look at cancer diagnosis. Thanks. So then what we were looking at another application of the sensor. We wanted to see if it could effectively look at how well a treatment was doing on a patient. what we had is 5 chemotherapeutic drugs were given to patients over 5 weeks, and you can see for each of the 5 chemotherapeutic drugs, there were distinctive drops, so it could reliably monitor how effective a cancer treatment was. And so what happens is this sensor, it's really revolutionizing how we look at cancer treatment and diagnosis, because compared to the current gold standard of protein detection in cancer, it's 168 times faster, over 26,000 times less expensive at 3 cents, and over 400 times more sensitive. And also, it has limitless applications. You switch out the antibody, and you can detect an entirely new protein, meaning you can look at other forms of cancer, but also you can look at cancer treatments effectively. You could look at cancer drug resistance, because these are caused by unique mutations in the DNA, producing a unique protein, which you can pick up with my sensor. Also, you can look at the effectiveness of a cancer treatment, meaning that we are revolutionizing how we look at cancer treatment, personalizing the treatment at a patient, so you don't have that conventional guess and check method. Also could look at other forms of disease, such as in food and water safety, E. coli, salmonella, rotavirus, and then also you could look at other blood pathogens such as AIDS, STDs, and all of those. And so it could operate in any setting, such as a regular checkup, but also in developing nations, revolutionizing and possibly saving thousands of lives in cancer diagnosis, treatment, and the biomedical field. Thanks.
There are many ways to compare the healthfulness of different foods. One can compare nutrient content, for example. So if you were interested in antioxidants, you might compare vitamin C levels. If you did that for our 2 most popular fruits, apples and bananas, based on vitamin C content, bananas would appear twice as healthy, 10 milligrams in a banana compared to only 5 milligrams in an apple. But vitamin C is just one of thousands of different phytonutrients in fruits and vegetables. Turns out the vitamin C in apples accounts for less than 1% of an apple's total antioxidant activity. Here's the total antioxidant content of a red, delicious apple. Here's how much the vitamin C in the apple contributes. You can hardly even see it. Even though there's only 5 milligrams of vitamin C in a small apple, it has the antioxidant equivalent of 1,500 milligrams of vitamin C. I've reviewed before how taking that much vitamin C straight in a supplement might actually have a pro-oxidant effect and cause DNA damage. But you can get 3 times the antioxidant power eating a single apple without the adverse effects. Of course, there's more than just vitamin C in bananas, too. In fact, I was surprised to see this study out of Harvard suggesting that not only blueberries and strawberries, but bananas were significant sources of anthocyanins, the red, blue, violet phytonutrients found in berries. Maybe I underestimated bananas. They are, after all, technically berries. Still, I'm looking at these 3 fruits and I'm thinking, I see some anthocyanins here and here, but not seeing much, red, blue, or violet here. Now, wild bananas are a different story. There's anthocyanins in blue, purple, orange-red, red-purple, and pink-purple bananas, right? But none in yellow. So the Harvard researchers were challenged on it, and they said, look, we just took values from the USDA, and it turns out USDA apparently made a mistake. No anthocyanins in bananas, and despite twice the vitamin C, bananas were beat out by apples in terms of overall antioxidant power. But that's just measuring the ability of these fruits to quench an oxidation reaction in a test tube. It'd be nice to measure actual biological activity. For example, in this apple study, they also measured the ability of apple extracts from both peeled and unpeeled apples to suppress the growth of human cancer cells growing in a petri dish, compared to control. Wouldn't it be great to be able to compare that kind of superpower between different fruits? Well, now we can. Here's a graph of cancer cell proliferation versus increase in concentrations of the 11 most common fruits eaten in the United States. They decided to use human liver cancer for this study. If you drip water on these cancer cells as a control, nothing happens, right? They start out powering away at 100% growth, and they keep powering away at 100% growth. And pineapples, pears, and oranges don't do much better. Peaches start pulling away from the pack. At high peach concentrations, cancer cell proliferation drops about 10%, but bananas and grapefruits work about 4 times better, dropping cancer growth rates by about 40%. Red grapes, strawberries, and apples do even better, cutting cancer cell growth up to half at only half the dose. But these 2 fruits are the winners, causing a dramatic drop in cancer proliferation at just tiny doses: lemons and cranberries. So if you look at the effective dose required to suppress liver cancer cell proliferation, apples are more powerful than bananas, but cranberries win the day. And there was no effective dose listed for orange, pear, or pineapple, since they didn't appear to affect this cancer cell growth at all.